This is Capacitance Lecture 2. Here we will put together a circuit with resistors and capacitors, and we'll look at the effects of charging and discharging times for capacitors. Prior to this, we looked at what capacitance is, capacitors in series, capacitors in parallel. We were able to calculate charge for each capacitor and voltage across each capacitor using the capacitance equation. We're going to keep using those, and again, I'm hoping that you see that everything that we learned prior to this about basic circuits still applies. We couldn't apply the current law because there is no sustained current flow, right? There is a buildup and a discharge, but that's all there is. But we will be using the current law as we bring in resistors. So let's do that. Let's look at a couple examples. So let's see, we'll put a battery here. We'll put a resistor. We'll keep it kind of simple. We'll put a resistor. We'll put a resistor. And we'll put a capacitor. Ooh, come here. We'll put a capacitor right there. And let's put some numbers to this. We'll make it a 12-volt battery. Make this 10 ohms. Make this 8 ohms. And make this 6 ohms. And we'll make this a 20 microfarad capacitor. So let's say we have this circuit. Not too pretty, but that's all right. Hopefully we could see all the values. And I want to know the capacitance. Not the capacitance. I want to know the charge and the voltage across this capacitor. So capacitors are devices that store charge. So there's a couple things to say, right? And let's say, just for the sake of argument, there was a switch right here, right? And if initially this switch is open and it's in this position, there's no current flow, then if there's no current flow, there's no way charges get to this capacitor. This capacitor would be fully discharged. If I close this switch, so now this switch is closed, well, now there's a path for current flow, which means the capacitor is going to charge. Now, there's a couple things, right? How fast is this capacitor going to charge? Well, that's going to depend on how fast the charges can get to it. So these resistors are certainly going to come into play while this capacitor is charging up. But this capacitor will charge up. But the other thing we know is that there is two paths for current flow. Certainly, we could have charges go to the capacitor, and we could charge up the capacitor, but that's not going to happen for a long period of time. That's going to, once it's charged, current's going to stop flowing. So there'll be charges that can take this path. But there's also charges that are going to take this path. And the charges that take the green path are just going to keep taking the green path, or there's always going to be charges taking the green path because that has nothing to do with the capacitor. It is a path just through resistors. So we could certainly argue that initially I would say more charges are going to take the blue path because they're trying to get from one place to the other, and they have this whole big area where electrons can leave from or electrons can pool on, right? But once more and more charges get on this capacitor, let's say more and more negative charges get on this plate, it's going to be harder and harder to push more charges there, which means more charges are going to start going through the 8 ohm resistor. So we don't really want to say a capacitor works like a resistor because they do very different things, right? A capacitor stores charge. A resistor opposes the flow of charges by changing the kinetic energy or the energy of the charges into heat, right? So I don't really expect the capacitor to get hot. I just expect it to store charge. I do expect the resistors to get hot, and I expect there to be a constant resistance through resistors. So what we would see is initially more charges going this way, and then we'd see more charges shifting and more going through here. Now, once this capacitor is fully charged, well, that means no more electrons, and there won't be a side of positive charge either, right? So once this capacitor is fully charged, this path is done, right? So I'm not saying the capacitor is not there. I'm saying there will be no charges going through that. So then now all we'll have is a path through just the resistors. So let's start thinking about this then. If this is fully charged, it's like it's not even there. And you'll see in questions, right? it'll say something like, here's a circuit with resistors and capacitors, and let's assume that this circuit's been running for a while. Well, that's telling you, hey, the capacitor's charged, right? It takes a certain amount of time to charge up, sure, but if we're beyond those, seconds that it usually takes, then it's charged. So if that's the case, the only path is this green path, and we can solve this, right? If we look at the green path, what do we have? Well, we have a total resistance, and they're all in series, so 10 plus 8 plus 6, 24 ohms. We have a total current, 12 volts divided by 24 ohms, 0.5 amps. And then I can find everything else. 0.5 times 10 is going to be 5 volts. 0.5 times 8 is going to be 4 volts. 0.5 times 6 is going to be 3 volts, and that makes sense. 5 plus 4 plus 3 minus 12 equals 0, so that works out, and there's 0.5 amps coming out of the battery. So we've looked at the circuit. Now, if we looked at the circuit and we understand Kirchhoff's voltage law, which again pops up, then we can do some things. Well, yeah, there's no current flowing through this capacitor anymore, but it's in parallel with this. This voltage minus this voltage equals 0. And again, the voltage law always holds true, whether there's current flow or not, which is, makes it extremely useful. So this capacitor must be 4 volts across it. Now, what else do we know? We know capacitance equals charge divided by voltage. So capacitance times voltage equals charge. So 20 times 10 to the negative 6 farads, which is the same as a coulomb per volt, times 4 volts. How much charge is stored in this capacitor? That would work out to be 8 times 10 to the negative 1, 2, 3, 4, 5, negative 5 coulombs. So now we know everything about this capacitor and everything about this circuit. We know the current and voltage of each circuit, so we can calculate the power if we wanted to. We know the capacitance of this, so we can measure the charge, right? So we can get all the measurements that we need. All right, so let's take a look at this circuit. Same type of situation. We have some resistors and we have a capacitor. Instead of using the symbol for resistor, what I put in place are light bulbs, which, there's different types of light bulbs now. But if we assume that these are like the old incandescent light bulbs, then we know that there is metal in there. That metal heats up, and it heats up so much it glows, right? So it takes electrical energy and turns it into heat. So it's essentially a resistor, right? Sometimes these are also drawn like this, right? Instead of drawing it like that, sometimes they're drawn with a little resistor inside, and then it goes around it, right? But lots of times you see it like this, which is kind of like the filament, and here's the glass around it. All right, so right now the switch is in the off position. And then at some point we're going to take it to the on position. But let's say it's in the off position, which means everything is unlit. There is no current flow. The capacitor is not charged. So simply, if there's no path for current flow from the battery to everything else, then nothing's getting electricity. Simple as that. Now, initially, we're going to assume the capacitor is discharged, and it's not charged at all. And then we are going to take this, and we are going to close the switch. Now, if we close the switch, couple things, right? First of all, when I look at it, this light bulb, I'm going to call this light bulb A. I'm going to call this light bulb B. I'm going to call this light bulb C. So first thing we know is all the current's flowing through A, right? If we use positive flow, it goes through A, and then it splits up, it goes through B and C. So regardless of what's happened to B and C, A is in series with the battery. A gets all the current. And I also know Ohm's law, current equals voltage times resistance. And if they all have the same, or let me say it differently, they all have the same resistance, 10 ohms, so voltage equals current times resistance. Well, A is going to get the most current. They all have the same resistance, so A is going to have the highest voltage. And just to say it again, power is voltage times current, all equations from past lectures. So if it's got the highest current and it's got the highest voltage, it's going to be the brightest light. Now we'll keep going with this and we'll look at this a little more, but what's going to happen when I close this switch, we're going to have current flow, right? We have two paths through current flow. We have a path through B and A, we have a path through C and A. And initially, the capacitor is not charged. So what are we going to see? We're going to see electrons start to pull up on this plate. We're going to see electrons leave this plate. So we're going to have flow through resistor C while this capacitor is charging, right? So when we first close this switch, we're going to have flow like this, and we're going to have flow like this. But as the capacitor charges, it gets harder and harder to put more charges on it, right? It gets harder and harder to put more electrons on the negative side, and it gets harder and harder to pull them off the positive side because that becomes more and more positive. It doesn't want to let electrons go anymore. So this second path right here is going to have current, but that current is going to gradually go down because this capacitor charges. When this capacitor charges fully, there's going to be no current flow through this. So this path is going to disappear. Then I'm just going to have flow through this. So if I had a question and it said, what's the current through all of these lights as soon as I take the switch to on, right? So we're going to say situation 1, and we are going to say that time equals 0, switch, whoop, there we go, switch to on. So as soon as we put that switch to on, well, what do we have? Well, if this isn't charged at all, then essentially it's easy for charges to build up on it. This offers, no resistance, or it doesn't, affect flow at all as soon as I close the switch. So I basically have 10 ohms here, and I have these two 10 ohms in parallel. So I'm going to have a circuit that's going to be this, a total resistance. Well, it's going to be 10 and 10 in parallel. It's going to be 5. That's going to be in series of this. So I'm going to have a total resistance of 15 ohms, which is now going to give me a total current of, let's see, it's going to be 9 divided by 15, 0.6 amps. And I know this one's going to get 0.6 amps, 0.6 amps, 0.6 times 10. This is going to be 6 volts, which means this is going to be 3 volts due to the voltage loop, and this is going to be 3 volts due to the voltage loop. And therefore, this is going to be 0.3 amps. This is going to be 0.3 amps. So we're going to go through quite a bit. So now, if I wanted to say, hey, which light bulb's the brightest? Well, that's the light bulb that uses the most power, converts the most energy per second. Well, this is power. It's going to be 6 times 0.6, 6 times 0.6, works out to be 3.6 watts. So this is going to be converted 3.6 joules of electrical energy into light or heat every second. This one's going to be 3 times 0.3. This is going to be 0.9 watts, and this is going to be the same. This is going to be 0.9 watts. So initially when I close the switch, this light's going to be bright. These lights are going to be significantly dimmer, but they're both going to be equal. Now, what's going to happen over time? Well, over time, this capacitor is going to charge up. And because this capacitor is going to charge up, less and less current flow is going to go through this branch, which means less and less current flow, this current's going to go down, which means this voltage is going to go down, which means this light's going to go down. So we're going to see C dim. Now we're going to see B change too, but we probably want to use a little math to see how B changes. So as time goes by, we wait and we look at this a significant amount of time later. So we'll say, well, and there's ways to figure out these times, which would be next. Well, after time equals 0. Well, what do we have? Well, after that time, this capacitor's charged. There's absolutely no more charges moving through this path, which means there's no charges moving through C. So for C, the current of C is going to equal 0 because the capacitor's charged, so we can't push any more charges onto it, which means the voltage of C equals 0, which means the power of C equals 0, which means that light is off. So as soon as we turn this switch on, this light's going to be on, and then it's going to fade away as this capacitor charges. All right, well then let's keep going. So essentially this path doesn't exist. Now I know the voltage of this capacitor because, well, let's do some math first, actually. So what's the total resistance? Well, the charges are all going to go through A, and then they're all going to go through B. So now A and B are now in series because this path, again, isn't a path anymore. It's essentially not there electrically. So I'm going to have a total resistance of 20 ohms, which means I'm going to have a total current. So now the current's going to go down because I have less paths, right? As soon as as we add paths, it is easier for charges to flow. Resistance goes down, current goes up, but I've taken a path away. So now the resistance actually goes up mathematically, and therefore the current's going to go down. So it's 9 divided by 20.45 amps. So resistor A gets all the current, 0.45 amps. And it's 10 ohms, so it's going to have 4.5 volts. So resistor A is now getting less power, which makes sense. There's less current coming out of the battery. So now the light bulb is essentially I'm going to write it all out, 2.025 watts. So the power of this light bulb goes down. Now, just to say, you say, well, when I go to a store, we could buy a 30-watt light bulb. And here the wattages are changing, right? You have no idea what that light bulb's going to use, right? When you buy something that's rated at 30 watts or 100 watts, that's saying, hey, if you use this the way we tell you, this is how much energy it's going to convert every second, right? So I don't know what the ratings of these light bulbs are. I just know that they're 10 ohms, and that's the only thing I can really control. So initially, as soon as I close the switch, well, before I close the switch, the light bulb's off, right? As soon as I close the switch, it's very bright, or it's bright. And then as time goes by and this charges up, it dims. Now, it doesn't go out. It just dims because there's still current flowing through it all the time. Now, I go to this one. Well, that one's in series 2, so it's going to be 0.45 amps, which means it's going to be 4.5 volts, which means it's going to be 2.025 watts. Which means that light bulb, which used to be relatively dim, 0.9 watts, is actually going to get brighter as this capacitor charges up. And when this capacitor is fully charged, both light bulbs will now be the same brightness. A got dimmer slightly, but definitely dimmer, and B got brighter, right? So by watching the light bulbs, we would know what's going on with the capacitor, and we could see, right? And I know C is out, so when the capacitor is fully charged, light bulb C is out, and the capacitor is not doing anything. I also know what? I also know if this is 4.5 volts, then the voltage across this, when fully charged, is 4.5 volts. And did I give I did not give a capacitance for this. So let's just say, let's just say that it's 1 farad. It's a big monster capacitor. So then capacitance equals charge divided by voltage. So capacitance times voltage is going to be charge. So it's going to be 1 coulomb per volt times 4.5 volts. So this is going to hold an enormous amount of charge, which is 4.5 coulombs of charge. Now, just to say that's a lot of charge. Sometimes in class, as a joke, I'll charge up one of my big capacitors, which is still not a farad, but I'll charge it up on a power supply. I'll use like a 20-volt power supply. I'll charge it up, and I'll just say, hey, that wire came off. Can you attach the wire across the 2 leads on the capacitor? And it'll make a nice popping noise, and there'll be some heat and some sparks coming off it. And it works out pretty well, right? 4.5 coulombs of charge, that's a lot of charge. So if we discharge this quickly, right, we're going to generate an enormous amount of current flow and heat for an extremely short amount of time. But there we go. Now we have everything for this after the switch has been closed for a long period of time. Now, I'm going to erase all this, and then I am going to look at one more situation, but I'm going to kind of clear this all up and kind of put back some of the things that that we have on there that we need. All right, so I've cleaned this up some. This is what would be happening if the switch was on. We know the voltage across each component, and actually just to fill it in, this would be 0 amps. This would be 0 volts, all things we said, but just to put it in. So in green, we have all the values for each component if the switch was on, and it was on after a long period of time, long enough to let the capacitor charge up. Now, what happens if we take the switch back to off? So now, I don't know, let's use this. We take this switch and we take it back to off. Well, a couple things we know immediately. If we take this switch to off, light bulb A has no path for current flow. So light bulb A will have a current of 0. Well, let's write it over here. Switch to off. So initially, as soon as we take the switch to off, the path through A is gone. We need a complete path of current flow. There is no complete path, so that means the current through A equals 0. And according to Ohm's law, if the current is 0, then the voltage is 0, and therefore the power is 0, which means as soon as I take this switched off, A goes off instantly. But this capacitor has charge, right? This is the positive. This is the negative. They are being stored there because the battery pushed them on there. But now I've broken connection with the battery. But this capacitor is still charged. So for a period of time, it'll now discharge because there's nothing holding them on here, but they're all stored there. So now all of a sudden I will have flow like this. And this flow will be there while the capacitor is discharging, right? Initially, there'll be a lot of flow because there's a lot of charges pushing on each other. As this capacitor discharges, this flow will go down. And that means if the flow goes down, well, then the current goes down. But as soon as we take the switch off, what do I have? Well, I'm going to not worry about this because that's not true anymore. And I'm not going to worry about this because that's not true anymore. But I essentially have 4.5 volts of this capacitor. And I have 2 resistors in series, so I have 20 ohms. So I have resistance total 20 ohms in this new path, assuming, right, that this is now not part of my circuit. And my circuit is now going to get charged by the capacitance. So I have a total resistance of 20 because it's going to go through 10 and 10 in series. I have a voltage of 4.5, so it's going to be 4.5 volts divided by 20 ohms. I'm going to have a total current of 1 second. There we go. 4.5 divided by 20. 0.225 amps. So now light bulb C gets 0.225 amps is our current. Our voltage is going to be 2.25 volts because Ohm's law. This one's going to be the same. It's going to be 0.225 amps. It's going to be 2.25 volts. That's the current. That's the voltage. And then if I multiply them together times 2.25, they are both going to be 0.5 watts. And this one's going to be 0.5 watts. So as soon as I take the switch to off, this light bulb goes out. This light bulb turns back on. Dim, yes, but it turns back on. This light bulb dims. And what's going to happen? Well, the capacitor is going to discharge. So as it's discharging, there's going to be less and less of a push. So less electrons are going to be moving around, right? And then eventually it's going to go dim or go out when the capacitor is fully discharged. So once the switch goes, so immediately, this is immediately, that's how you spell it, right? And then after a period of time, A's not getting any current because it's not hooked up to a circuit. The capacitor is going to discharge, so it's not going to have anything left to supply. So C is not going to get any current, which means B, which was this one right here, B is not going to get any current. So after a period of time, everything is going to go out. So there's 2 examples of capacitors in circuits. We can calculate different values for different times. And we can calculate for in between those times, which is what we're going to look at next. So let's clear this. We want to start looking at these times. And we're not going to spend a lot of time on it. I'm simply going to give you the equation and explain the equation. So initially, the capacitor works as a short, right? It doesn't offer any resistance or doesn't offer any opposition. There's no forces trying to oppose the charges moving around. As time builds up and the capacitor becomes fully charged, well, then it's kind of like an open. It breaks that path. Once it's fully charged, that path doesn't exist anymore and no charges will move through that path, right? So it goes from offering nothing in opposition to completely stop and flow. But this takes time. And if we think about it, if I have a circuit, here we go, if I have a circuit and I am charging a capacitor and I have a resistor, come on, there we go, and I have a capacitor, my drawing's getting worse as this lecture goes. And I want to see how long it takes for this capacitor to charge up. Well, a couple things matter. One thing that matters is how big of a capacitor is it, right? If it's a tiny capacitor, well, it's not going to take long to charge it up. Or if it's not a very good capacitor, it's going to not take a lot of time to charge it up. If it's a really good capacitor and holds an enormous amount of charge, well, then that's going to take longer to charge up. So the capacitance matters, right? The more capacitance we have, the more charges it can hold, therefore the more time it's going to take to put all those charges on there. If you imagine charges were people, and this could only hold one person, well, it's not going to take long to charge it up. If this was really good and it could hold 1,000 people, well, then it takes a while for those 1,000 people to get there. So the capacitance determines how long it takes. But the other thing that matters is the resistance in that path. Because the more resistance, the more opposition to flow, which means it gets harder for these charges to get to where they're going. So that's going to slow it down too. So as this goes up, it takes more time for this to charge. As this goes up, it also takes more time for it to charge. And this holds true for discharge also, right? If a capacitor has a high capacitance and it's fully charged up, that means it's got a lot of charges. So it's going to take a while to get rid of them, right? And if the resistance is high, it's going to take long for the charges to move around, which means it's going to take a while for it to discharge. So everything holds true. So the first thing that we could say is we have this term, which is a time constant. And a time constant is going to help us determine how long it takes for a capacitor to charge or discharge. And either way, this time constant equals the resistance of the path times the capacitance of the capacitor. And this isn't the time to charge or discharge. This is what we call the time constant. Then we're going to have to use this fancy equation underneath to figure out where we're at. But what we do know is 5 time constants, I'll write it up here, 5 time constants is fully charged or fully discharged. So we're going to say more about this to explain why we just can't give a time. Because we can give a time, right? If I said, hey, how long does it take to charge the capacitor? Well, I could find the time constant, multiply it by 5, and say, okay, there we go. That's the time it takes. So we can figure out how long it takes for this whole process. But the other thing that this equation allows us to do, it allows us to look at it along the way. So if I had this circuit right here, and I looked at this, and I looked at the voltage across the capacitor, or I looked at the current, right? I could kind of look at this 2 different ways. So let's look at the current of the battery. Now, I know initially when the capacitor is not charged, there's going to be a lot of current, right? So it's going to be up here. And I'm going to say current max. It's going to be at the maximum amount because when the capacitor is not charged at all, it's not trying to oppose charges moving around, works out just fine. And I know after time when the capacitor is charged, well, the current's going to go down to 0. But how is this going to work? Well, it's going to work not linear. Initially, there is no opposition to flow by the capacitor, but as the capacitor charges, it gets harder and harder and harder and harder. So its opposition increases, right? Which means getting those last ones on takes a while. So what we're going to see is we're going to see a very quick drop in current flow, and then it's going to work out like this. That's how current flow is going to go, right? And it's going to reach 0, and it's going to reach 0 after 5 time constants, right? So this would be 1, 2, 3. That worked out pretty good. 4, right? It's going to work like that. So it's not going to drop linearly. It's going to drop exponentially, if you will. If I looked at voltage, And not really voltage of the battery, because voltage of the battery is not going to change. But let's say we looked at voltage across the capacitor. Well, initially, the voltage across the capacitor is going to be 0 because it's not charged. As we put more and more charges on it, the potential energy per charge is going to build up. So it's going to reach a maximum, and that maximum is going to take 5 time constants, and that maximum is going to be the voltage of the battery. Now, again, it's not going to be linear because initially it's easy to put charges on there, so the voltage is going to go up a lot. And then as it gets going, it gets harder and harder and harder to add more voltage or add more charges, so it's going to have a smaller and smaller effect. So it's going to work out something like this. Now, discharge is the same type of thing. So how do we know where we are in time? So that gives us this equation right here, where we could say the voltage across the capacitor, let's go back to this drawing. There we go. So this is the capacitor. This would be the voltage across the capacitor equals the voltage of the battery, which is the maximum it's going to get to, and then it's going to be times kind of all of this stuff. Now, what is that? Well, T, this T right here, is the time in question. We want to know what the voltage across that capacitor after 3 seconds, something like that. So that's not the time constant. That's just what time do we want to know what the voltage is. This is T, the time constant. So they just wrote it as R times C. This is the actual voltage of the battery, or the maximum the voltage can get to. All right, so let's try this out. Let's say that this is a 12-volt battery, so that's the highest voltage that this capacitor is going to get to. When it's fully charged, it's going to be 12 volts because there'll be no current flow. Current will be 0 here, voltage will be 0 here. This will have all the voltage, and there'll be no current still. And let's say that this is a 500 ohm resistor, and let's say that this is a 20 millifarad capacitor. All right, so our time constant is going to be 500 ohms. And again, ohms is the only time I don't really care about unit analysis. Something like this, if you look, they'll make up some units for ohms. And I'm not saying it doesn't work. It's just not what it is. 20 times 10 to the negative 3 farads. And that's going to give me a time constant, right? 500 times 20 to the negative 3. 500 times 20... 20 to the negative 3 works out to be a time constant of 10, right, there we go, 10 seconds. So the time constant is 10 seconds. So I know that this capacitor is going to be fully charged after 50 seconds. But let's say I want to know, hey, what's the voltage across this capacitor at 30 seconds? So I want to ask the question, what is the voltage of the capacitor? And then if I knew the voltage of the capacitor, I can know how many charges are stored there after 30 seconds. I know it's not the full 12. I know it's not 0. It's somewhere in between. So how would I do this? Well, the voltage of the capacitor would equal the total voltage it could be, which is 12 volts, 1 minus E raised to, well, it's going to be negative 30 seconds, because 30 seconds is the time I care about, divided by 10 seconds, because 10 seconds is my time constant. So there's my equation. Now, just before I do anything, because we're not going to do too many examples of this one, this right here basically gives me the percentage, right? Now, I don't want to say it exactly does, but it does. Right? This is going to give me the percentage. How much of the total is there? And then I can take that percentage and I can multiply it by 12, and that's where we're at. So if I do this all out, what do I get? Let's see. Let's going to be 12 volts times this is going to work out to be 0.95, and then I multiply that by 12. It's going to be at 11.4 volts. It's going to be almost fully charged, but again, we know the charging follows this pattern, which is right here. So, I mean, after the first time constant, it's already at 63.2%, right? And after the third time constant, it's pretty much at 95%, which is just what this graph is showing us. So, so it sounds right. So we're going to be at 11.4 volts, and then we can calculate everything else we need. So clearing off some of this stuff, this equation, now that we've defined each term and kind of looked at an example, this equation is for a capacitor when it's charging. The capacitor when it's discharging is the exact same equation, except it's not 1 minus, right? And that's because the voltage is going down, not up. So either way, this area is giving us that percentage. And then we take that percentage and we multiply it by the total, and that's how much voltage is there at this point, right? When we're discharging, in parentheses, it's E raised to the time divided by the time constant. When we are charging, it's 1 minus E raised to the time minus the time constant, right? So really the only difference is once it's this, once it's 1 minus this, which makes sense because sometimes the voltage is going up. So this is what we do. Sometimes the voltage is going down. This is what we do. Actually, just the opposite. Sometimes the voltage is going down here. Sometimes the voltage is going up here. So that's where the 1 minus comes in, right? Because the E will give you a percentage. But we have to use that percentage 2 different ways. Okay, so that is circuits with capacitors and resistors. And that's also how to figure out what state the capacitor is in while it's charging and discharging.